Isaac Newton's definition number 4 concerns itself with what we now refer to as Newton's first law of motion. There's very little in any of the guides. Chandrasekhar, for example, he doesn't really comment anything about this. He thinks that it's entirely self-explanatory. There's nothing further to add. But there are actually some details that we can tease out, and there are certain things about Newton's 4th definition that we can demonstrate with experiment. So let's have a look at what it says. Definition 4. An impressed force is an action exerted upon a body in order to change its state, either of rest or of moving uniformly forward in a right line. This force consists in the action only and remains no longer in the body when the action is over. For a body maintains every new state it acquires, by its vis inertiae only. Impressed forces are of different origins, as from percussion, from pressure, from centripetal force. An impressed force. What does Newton mean by these words? I think he just simply means an applied force. Recently, the language used to describe Newton's first law of motion has shifted to referring to an unbalanced force. What it of course means in old money is that it is a resultant force that causes the state of motion to change. But here Newton is more general, talking about just this impressed force, a force that is applied to an object such as a push or a pull. Here we have a cart attached to a string. It goes to a pulley at the end of the table, and there are some weights. If I let the weights fall, then there is going to be an impressed force, and it's going to change the state of motion of this cart. Here we go. Ta-da! So what about this impressed force? Well, Newton thinks that it can do one of 3 things. The first is that it can change the state of motion from rest to something else. So right now, this car here, it is in a state of rest relative to me. And so when there is an impressed force, which is going to occur when this propeller starts to turn, blowing the air through and pushing the car the other way, an impressed force, its state of motion is going to change. The proof of that will be that it, over there, will no longer be stationary. That was dangerous. But what you can see is it moved. Its state of motion changed only when the force was being applied. The second thing that Newton speaks of is when moving uniformly forward, that state itself can be changed. Now there's 2 ways it could be changed. Your motion could increase in the direction you're going, or it could decrease. You could accelerate, or you could decelerate. So let's have a little look at those 2. Right, okay, check out this. I think this is apparatus that would test the next part of the definition. So Newton said that this impressed force would, 1, change the state of rest, so stationary to not stationary, but 2, from moving uniformly forward. So how can we see that a force changes that uniform forward motion to a different uniform forward motion? For example, the car going faster. So here I have an elaborate setup. And what it is there's a cart here, and it's going to drive through these 2 light gates. And we're going to be able to measure how fast it's going there, how fast it's going there. But I want the car to have some initial velocity. It's already got some velocity from somewhere, and then a force applies. Can we make it speed up when it already has velocity? Well, of course we can. And the way we're going to do that is as follows. I'm going to release it from this ramp. And it might look a bit strange, but to actually get it to come down the ramp at the right moment, I'm going to hold it up the ramp with this well, two meter sticks that are basically sellotaped together. I'm going to allow it then to come down the ramp, and when it gets to the bottom of the ramp, the prediction is that at that point its weight will not be accelerating it should then be moving at constant speed from here to here. But when it gets into this zone, what I then want to do is I want to drop the weights, and they're attached to the front of the car. And so what this should do is it should then, having gone from moving at a constant velocity, there should then be a force applied to it somewhere in this region here. And what we should find, if Newton was right, is that it has indeed increased in velocity from the original lower velocity that it had. Well, let's give it a go. 3, 2, 1, and go. Oh, that was good. But no, there was no readings recorded on there. Obviously, my light gates were too high. Right, in which case we're going to have to repeat this again with lower light gates. Okay, I think the light gates are lower now, so let's put this system back together and hope for the best. So push the cart up there, hang this on here, and get it taut. We'll go in 3, 2, 1. Okay, it went through the first light gate at 1.2 meters per second, and then when the force applied, it upped that velocity to 1.46. Ha! So there we go. Newton was right. If you apply a force to an object that's already moving, it's going to accelerate it. Now, of course, this is applying a force in the same direction as it's going. The other thing that, of course, could happen is if the force applies the other way, then it could actually slow it down. So is there a setup that can show that? Right, I think this will do it. So same setup with the light gates as before, but this time I'm going to move the two light gates closer together. I've got the car here ready to go, and what I'm going to do is I'm just going to make sure that the interrupt card is on the right side like this, so that as it rolls down, it should go through those light gates. I'm trying to steer it. But now what I've got is I've got the string attached to the weights over here. And so what's going to happen is I'm going to let the car roll down the slope. When it gets to the end of the slope, I'm going to allow weight to come onto this, which should apply a force backwards as it is moving forwards. What we should see is that the velocity of this, of the car here, is greater than the velocity of it there, that the actual state of motion has been changed by decreasing the velocity. 3, 2, 1. Okay, brilliant. So when it went through the first one, it was moving at 1.4 meters per second. When it went through the second one, it was going at 0.8. So what had happened here is when the force was being applied backwards to the direction of motion, it was changing the motion of the car, but this time it changed it to a lower value of velocity. Now there's one more thing that Newton mentions. He says that a force like this, an implied force, could actually change the right line of an object. So is there an experiment we could do here that demonstrates an object's right line being changed by a force? And I think that there is. Righty-ho. So Newton said that this impressed force could change the right line of an object's motion. Well, here is the right line of an object motion when there is no force. So this object is accelerating downwards, and off it goes in a straight line towards you. What I'm going to do now is I'm going to tilt the table so that there is now a force acting at right angles to the direction it's going. So exactly the same, except now the table is tilted. So the ball's going to be going in its right line that way, but there's now also going to be a force acting at right angles to the directions it's going. And so hopefully What this will prove is that the right line of an object can change when there is an impressed force upon it. So let's have a look. Yeah! Oh, I love it when it works. Newton, with his impressed force, said that the force consists in the action only, that when the force was no longer applied, the effects of the force would no longer be felt. And in the previous two parts of the definition, he pointed out that an impressed force would have the effect of changing the motion. So what we're expecting is that after a force has been applied and it is no longer applied, we should no longer see any further changes in motion. And he says it remains no longer in the body when the action is over. So here is an experiment that should demonstrate that same thing. So what we have here is we have the trolley going to go through the pair of light gates. It's going to measure the velocity twice, and the trolley is going to be pulled initially by some weights on this pulley just here. But this time the weights are not going to continue to fall towards the floor. Oh no, they are going to land on this chair, and at that point they take themselves out of the equation. They no longer are pulling on the string, there's no longer a force applied to this, and what we should see is actually this is no longer accelerating. It might actually be decelerating due to friction, but we'll ignore that. It will no longer be accelerating. So let's give it a little go. Find my stylus to wake up the data logger. Okay, let's go. So we're going to put this on here, set it all up, ready to go. Here we go. Oh, look at that! So it went through the first light gate at 0.5 meters per second and through the second light gate at 0.497. Basically, the tiniest bit of friction has slowed it down, but there was nothing continuing to speed it up once that force was no longer impressed. The very final part of Newton's fourth definition talks about ways in which forces could be acting differently to each other. And he describes that this object here, it maintains every new state it acquires by vis inertiae, that basically the inertia of the object will mean that it will continue at whatever velocity. These days we look at it more as a case of there's nothing to change it, so it just carries on doing as it is. But he talks about the impressed force coming of one of three different types. The first he describes as percussion. And so we've got a very good example of percussion here. We've got a spring-mounted trolley, so you press the button and it presses a sudden ejection of that there, and I've got it up against something that is fixed, and what I notice is if I press it, percussion is a force that then accelerates this object. But he lists two more. He lists pressure and he lists centripetal force. So let's go have a look at those two. So this is a really good example of pressure. It's the fan car again. Unlike percussion, which is going to deliver a single impact of force that instantaneously is going to trigger a motion change, this continuously applies a force. And so the motion change is going to be continually added to. It means it's going to continue to accelerate. Let's give it a little go. This is what Newton calls pressure. On the floor, turn the fan on. It goes. Gosh, look at it go. Pressure is constant. Oh, that sounded painful. So what about centripetal force? A force acting at right angles, a centre-seeking force. Well, let's give it a go. I've got a constant velocity car here, and there's a string attached to this table. Let's see what it does. That's amazing. The constant action of this force coming towards the centre of the circle is resulting in the car's motion continually being changed. that the direction in which it is travelling is changing, which was the third result. So when you read about Newton's first law of motion, don't forget all of the extra detail that Newton packed into it to give a full understanding of how forces work.